Hello and welcome. Welcome to the Deep Learning course. And in today's lecture, we will cover the topic of Theorem of Multilayer Perceptron. So let's start. If you remembered, previously we have covered the topic of multilayer perceptron, where at that time we mentioned that a multilayer perceptron consists of more than just the input and the output layers, because it also includes one or many hidden layers, and the hidden layers are located in between the input and the output layers. And at that time we have also mentioned that the hidden layers includes a certain number of neurons which is decided when the multilayer perceptron is designed. So let me revise it graphically. If we have a multilayer perceptron having one input layer, if this is the input layer, okay, and one output layer, this is your hidden layer, sorry, this is the hidden layer and one output layer. And in between these two layers, the input and the output layers, there are one or many hidden layers, and in these hidden layers there could be certain number of neurons also included. Okay, so in today's lecture we will see the theorem of multilayer perceptron, which is used to decide the number of neurons in these hidden layers. Okay, so let's start. According to the theorem of multilayer perceptron, if there is a Boolean function such as the AND gate that we have covered previously, or the OR gate, or the exclusive OR gate, or any Boolean function that will be having n inputs, then it could be represented by a multilayer perceptron that will be made up from one hidden layers with 2 raised to the power n neurons and one output layer with just one neuron. Okay, so basically the theorem of multilayer perceptron says that if we have a Boolean function with n inputs, then it could be represented or it could be solved with a multilayer perceptron made up from just one hidden layer with 2 raised to the power n neurons and one output layer with just one neuron. Okay, so if we have such a Boolean function such as the AND, or exclusive or not anyone, when there will be we two inputs, then the n will be having a value is 2, then the multilayer perceptron that will be designed to solve such a Boolean function will be made up from one hidden layer with 2 raised to the power n neurons. So in this case, 2 raised to the power n will be equal to 2 raised to the power 2, which will be equal to 4. Okay. So such a Boolean function with only two inputs get to be solved with a multilayer perceptron having 4 neurons in the hidden layer and 1 neurons in the output layer. Okay. So the designed multilayer perceptron could look something like this. This is the hidden layer with 4 neurons, 2, 3, 4, and one output layer with just one neuron, and there will be the input layer that will pass these two inputs as x1 and x2. This is the input layer, okay, and this is the hidden layer, and this is the output layer. So this is the proposed multi-layer perceptron to solve a Boolean function with just only two inputs. And you can consider each of the neuron in the output and in the hidden layer as a standalone perceptron, which performs a weighted aggregation, and then to the calculated weighted aggregation it applies some function, a thresholding function, to decide the final output. Okay, so this is basically a multi-layer perceptron to solve a Boolean function with two inputs. Now let's see how to design a multi-layer perceptron to solve a Boolean function with three inputs. So in this case, your hidden layer will be having 2 raised to the power 3 neurons, which is 8, and one output layer that will be always that will be always having one neuron. So when you will be having 3 inputs, you will can solve such a Boolean function with a multi-layer perceptron where the hidden layer will be having 8 neurons and the output layer will be having 1 neuron. So it will look something like this. If this is the input layer having 3 inputs as x1, x2 and x3, it could be solved with a hidden layer, with a multi-layer perceptron having one hidden layer where there will be 8 neurons, 1, 2, 3, 4, 5, 6, 7 and 8, and one output layer with just one neuron. This is the output layer. Okay, this is the hidden layer and this is the input layer. And again, consider each neuron in the hidden and in the output layer is a standalone perceptron. Okay, and this will be passed in this way. So when you will be having 3 inputs in your Boolean function, then you can solve such a Boolean function with a multi-layer perceptron having one hidden layer with 8 neurons and one output layer with 1 neuron. Okay, so if we have a hidden layer of 2 raised to the power n neurons, we can represent any Boolean function of n inputs with it. So if there are n inputs combinations, then each of the 2 raised to the power n neurons in the hidden layer will simulate 1. For example, if we have 2 inputs, n is equal to 2, okay, such as the x1 and x2, it will have possible combinations as 0, 1, 0, 1 and 0, 0, 1, 1. So such a Boolean function could be solved with a multi-layer perceptron having one hidden layer, this is the input layer, having 2 raised to the power n neurons, and one output layer having one neuron. This is the output layer, this is the hidden layer, and this is the input layer. Okay. So such a Boolean function could be solved with such a multi-layer perceptron having one output layer having one neuron and one hidden layer having 2 raised to the power n neurons, where in this case n is equal to 2, so it is equal to 4. So in this case your hidden layer will be having 4 neurons as 1, 2, 3 and 4. So is there are two there are two inputs, so there are a total of 4 input combinations, and each of the 2 raised to the power n hidden layer neuron will simulate 1. So we have 4 neurons in the hidden layer, and there are a total of 4 input combinations for 2 input. So such as, for example, if you consider this combination could be simulated through one neuron among these 4 neurons, and the other one could be simulated through one another neuron. The third one input combination could be simulated through some another neuron in the hidden layer, so on and so forth. Meaning that the one neuron in the hidden layer will simulate one combination, okay, one possible combination. And just to note one other thing, because there are 2 raised to the power n neurons in the hidden layer and one bias that we have covered in the perceptron lecture, where we have mentioned that instead of starting the inputs from x1, it's better to start it from x0, where the first input x0 is set to some constant known as bias. So if we have 2 raised to the power n neurons in the hidden layer plus one bias, so that will be the total number of neurons in the hidden layer. And they are not necessary, they are not always required, but they are sufficient to solve any Boolean function with it. It is possible that the same problem, the same Boolean function could be solved with neurons less than 2 raised to the power n in the hidden layer, where 2 raised to the power n, which are the neurons, plus 1, which is the bias. But it will be solved definitely with 2 raised to the power n neurons in the hidden layer. Okay. But the computational complexity of the neurons in the hidden layer is very important, because as the number of inputs n is going to increase, it also going to cause the number of neurons increases in the hidden layer. For example, if we have n is the number of input and 2 raised to the power n is the number of neurons in the hidden layer, if there are one input, it could be, then in the hidden layer there will be 2 raised to the power is equal to 2 neurons. When there will be 2 inputs, then in the hidden layer there will be 2 raised to the power 2 neurons. The hidden layer, which will be 4. When there will be 3 inputs, then in the hidden layer there will be 2 raised to the power 3 neurons, which is equal to 8. And similarly, when there will be 4 inputs in the Boolean function, then in your hidden layer there should be 2 raised to the power 4 neurons, which is 16, so on and so forth. So you see, when the number of inputs is going to increase, it also causes to increase the number of neurons in the hidden layer. And the number of neurons in the hidden layer is very important, because it is the one thing that is causes to increase the computational complexity of your multi-layer perceptron, that makes your multi-layer perceptron computationally too much expensive to train. Therefore, if it is possible to find a multi-layer perceptron solution for a Boolean function with the lowest number of neurons in the hidden layer, less than 2 raised to the power n, then you should go with it. Okay. So this was about the theorem of multi-layer perceptron. I hope you will have liked today's lecture. If you have liked today's lecture, please subscribe the channel, share the lecture with your friends, and see you in the next lecture. Bye.